Hi, today's topic is theoretical knowledge of electrical components, which can be capacitors, inductors, diodes, relays, and transistors. And there are going to be also a series of practical exercises designed to test understanding and problem solving skills. This time, we're going to solve 14 questions, all related to capacitors, inductors, diodes, and relays, together with transistors. Let's begin. We have a circuit. The question is, what is the total capacitance of the circuit? The question gives us all the capacitance of all three capacitors in parallel circuit. So to calculate the total capacitance, we simply need to add all the capacitors together, which is going to be C total equal to C1 plus C2 plus C3, which will be 2 millifarads plus 3 millifarads plus 5 millifarads. If you sum it up, you will get 10 millifarads. And this is our answer. In question number 2, we have a circuit. The question asks, what is the charge stored in the capacitor? So we're looking for Q value. In the formula, which is Q equals to V multiplied by C, where Q stands for charge in coulombs, V stands for voltage in volts, and C stands for capacitance in farads, we are looking for Q value. So let's write down what information we are given. We are given volts, then we are given capacitance, which is 10 millifarads, and we are looking for Q value. The formula that we're going to use is this one. Q equals to V multiplied by C. If we calculate it, it's going to be 12 volts multiplied by 10 millifarads. In the end, we're going to get 120 millicoulombs. So this is going to be our final answer, 120 millicoulombs. In question number 3, we have another circuit. The question says, how much energy in joules does the capacitor store? So the formula we're going to use is E equals to 1 over 2 C multiplied by V squared, where E stands for energy in joules, C stands for capacitance in farads, and V stands for voltage in volts. So let's write down the information we are given. First of all, we have voltage, which is 10 volts. Then we have capacitance, which is 4 millifarads. If we're going to change it to scientific notation, we're going to get 4 multiplied by 10 to the power of minus 6 farads. Then we're going to use the formula E equals to 1 over 2 multiplied by C multiplied by V squared. If we're going to write it down, it's going to be E equals to 1 over 2 multiplied by 4 multiplied by 10 to the power of 6 multiplied by 10 squared. If we're going to calculate it, we're going to get 2 multiplied by 10 to the power of minus 4 joules, which is our answer. Question number 4 is also about circuit. Here we have one, and the question asks, what is the total inductance of the circuit? This is a simple one. So to get total inductance of the circuit, we just need to sum everything up. So in this case, L total, L which stands for inductance, is going to be equal to L1 plus L2 plus L3, which is going to be 1 plus 2 plus 3, which is going to be equal to 6 henries. And this is our final answer. In question number 5, we have another circuit. The question says, if the current through a 2H inductor increases at a rate of 3 amperes per second, what is the EMF generated? In this case, EMF stands for electromotive force. The formula to find the electromotive force is going to be EMF equal to negative L multiplied by di over dt. In this case, L stands for inductance in henries. Di over dt stands for rate of change of a current, and it is measured in amperes per second. So let's write down the information we are given, which is going to be inductance that equals to 2H and the rate of change of a current, which is going to be 3 amperes per second. And we're looking for EMF. So the formula we're going to use is the same one. Negative L multiplied by di over dt. If we're going to apply the formula, we're going to get negative 2 multiplied by 3. Then we're going to get electromotive force is measured in volts, which is going to be our final answer. The reason why we got negative number is because electromotive force opposes the change in the current, according to Lenz's law, which totally makes sense. Here we have another circuit. So the question is, a voltage of 24 volts is applied to a 4H inductor for 2 seconds. What is the value of the current through the inductor at the end of this period? So the formula we're going to use for this one is the same that we used for the previous question. However, in this case, we're going to rearrange it and add one more formula. So if we're going to write down the information given, it's going to be voltage, which is going to be 24 volts, L, which is going to be 4H, and T, which is going to be 2 seconds. So we're looking for I, which is current through the inductor. In this case, we're going to use two formulas. The one we're going to rearrange from the previous question, which is di over dt equals to V over L. And for I, it's going to be delta I equals to di over dt multiplied by t. If we're going to apply the formula, di over dt is going to be 24 over 4, which is 6 amperes per second. And for I, we're going to put 6 times 2, which is 12 amperes, which is our final answer. Here is number 7. It says, if a voltage of 0.7 volts is applied in the forward bias direction to a silicon diode, is it in conduction or cut off? So in forward bias, the applied voltage will go through the diode, it is true. However, the voltage drop that usually takes around 0.7 volts will consume all the voltage applied. This will mean that no voltage is going to be received. This means that diode will be in neither conduction or cutoff. Question 8. A silicon diode is in conduction with a current of 10 milliamperes. Considering a typical voltage drop of 0.7 volts, what is the voltage drop across the diode? So let's write down what we know. Our I is equal to 10 milliamperes, which is the same as 0.01 amperes. Then we have VF, which is forward voltage, and it's going to be our voltage drop. And then we're looking for the overall voltage drop across the whole circuit. So the thing is that in this case, VF is actually equal to V drop. So the thing is that when diode is forward biased, the voltage across it is approximately equal to its forward voltage. So in this case, it is quite easy. We're just gonna add everything up, which is gonna be 0.01 plus 0.7, which is equal to 0.71 volts. And this is our voltage drop. So the formula we're going to use is R equals to V over I, where V is voltage, of course, and I is current. R stands for resistance, and it is measured in ohms. So if we're going to write things down, we have voltage, 10 volts, and our current, 1 milliampere, which is in scientific notation equals to 1 multiplied by 10 to the power of minus 6 amperes. So we're gonna use this straightforward formula, nothing hard. R equals to V over I. And if we're gonna use this formula, we're gonna get 10 over 1 multiplied by 10 to the power of minus 6. And if you're gonna calculate it, you're gonna get 10 to the power of 7, which is our answer. The other way how we can answer it is 10 milliohms. So in question number 10, we have a circuit again. It says, if a relay requires 0.5 watts of power to activate and is powered by a 12-volt source, what is the minimum current needed to activate it? So in this case, we will use a simple formula as well. In this case, we will use a simple formula as well, which is going to be P equal to V multiplied by I, where V stands for voltage in volts, and I stands for current in amperes. P P in this case stands for power in watts. So if we're going to use this simple formula with the information given here, where P equals to V multiplied by I, we will need to rearrange the formula because we are looking for I. So in this case, I will be equal to P over V. If we're going to use the formula, we will get 0.5 over 12. If we calculate it, we will get approximately 0.0417 amperes. In this case, we can say that it's 41.7 milliamperes, and if we're going to follow the one significant number rule, we can say we have 40 milliamperes, which is going to be our final answer. In question number 11, we have a simple circuit with a relay box this time. The question says, if a relay with a coil resistance of 240 ohms is powered by 12 volts, how much power does the coil dissipate? So we're going to use a simple formula again. P, which is power, equals to V squared over R. Voltage and resistance. So we are given R, which is 240 ohms, and voltage, 12 volts. We're looking for P, power. So with the formula given, we will just apply it, which is going to be 12 squared over 240. If you will calculate it, you will get 0.6, which is going to be watts. And this is going to be our final answer as well. Question 12. So in a BJT, which is bipolar junction transistor, so if the base current is 20 milliamperes and the transistor has a current gain beta of 100, what is the collector current? So in this case, we're going to use this formula. IC equals to beta multiply by IB. In this case, IC is collector current, while beta is current gained off the transistor. Also, IB is base current. So, with this being said, let's solve the question. We have beta, which equals to 100. IB, which equals to 20 milliamperes. And IC, which we're looking for. If we're going to use the formula, and we're going to apply it, IC will be equal to 100 multiplied by 20 milliamperes. In this case, it is not necessary to transfer amperes into anything else, so we will not do it. We will get 2000 milliamperes. Just don't move, beach. The reason why we don't need to change milliamperes into anything else is because beta doesn't have any identification. question number 13, which might be a bit hard. So, considering a BJT transistor with a VCC of 5 volts, VBE of 0.7 volts, a desired collector of 10 milliamperes, and beta of 100, what should be the base resistance? In this case, we're going to use a very scary formula, which is RB equals to VCC minus VBE over IB. Here, RB is resistance of a base, VCC is collector supply voltage, VBE is base emitter voltage, and IB is base current. So we're given IC, which is 10 milliamperes, and we're given beta, which is 100. So we're going to use two formulas, which is going to be IB equals to IC over beta. And we're also going to use RB equals to VCC minus VBE over IB, which was presented earlier. If we're going to use both formulas, we're going to first find the base current. Let's do it. It's going to be 10 milliamperes over 100, which is going to be 0.1 milliamperes. And then we're going to use the other formula, which is going to be 5 volts minus 0.7 volts over. By the way, this is going to be 100 actually. So we're going to use this 100 right here. And we're going to get 43 kilo ohms, which is going to be our final answer. So question number 14 is similar to question number 7 we had before. So the question is, if the base emitter voltage of a BJT transistor is less than 0.6 volts, is the transistor in cutoff, saturation, or the active region? So in case base emitter voltage is lower than previously mentioned 0.7 volts, which is the voltage drop for silicon BJT, the transistor is cut off.